Welcome everybody. So let me just share my screen as we're going, and there we go. All right, hopefully you can see my presentation. So my talk, really, the theme that I want to pick up and kind of continue from Dave's talk is really fundamental. What he's talking about is experimentation, is about working in a more, what I would think of as kind of scientifically driven approach to determining and making decisions. I think, I'm biased of course, but I believe that continuous delivery was an important discovery that we made during the course of this century in software development terms, because I think it kind of grew out of ideas of extreme programming, but it's fundamentally about kind of engineering principles. It's about applying scientific style reasoning to solving practical problems in software development, and that's kind of my theme. So I've done one of the things that I tend to do these days, which is I've got a slightly clickbaity title, which is scaling up, because everybody's interested in scaling up, and I am going to talk about that. But I want to sort of talk a little bit about the philosophy of that, and what it means to get, and what engineering means, and how we can apply that kind of thinking to help us to scale up. I think an important place to start and to think about is thinking about what our problem is. And often when we think about the difficulty of solving problems, we're worrying about the stuff that we can't afford to get wrong, and the complexities, the technicalities of producing things and that sort of stuff. And this has almost nothing to do with us. This is not our problem in software. Our problem is entirely different. We have some code that represents the systems that we create, and that code through some way or another turns into a stream of bytes ultimately that is deployed to one or many computers. Now, one of the things that's weird about that and unusual about that compared to more conventional things is that for essentially free, we can duplicate that stream of bytes. That means that we, at the push of a button, we can generate as many copies of that stream of bytes, that system, as we like. So essentially, we don't have a production problem ever. Ours is always a different kind of problem. Ours is a problem of learning, discovery, exploration, and not a problem of production engineering. So we need to think about this differently. So this means that applying ideas, production line style thinking, is the wrong thing to do. This is not about trying to discover cookie cutter solutions that are going to churn out, repeatable widgets. Our stuff's never repeatable. If it's repeatable, we just clone the sequence of bytes for free and we don't have to do anything else. Our stuff, in terms of software development, is always about, an original piece of work at some level or another. And so those kinds of old-fashioned approaches, those ways of thinking about things, don't apply to software. So software development is an exercise in learning and discovery. And what that means is that if we want to be able to become good at it, we've got to become world-class experts at learning and discovery. That means we need ideas like these. We need to be working iteratively, so we have more opportunities to learn. We need to gather feedback, as Dave was talking about, so we've got data on which to make decisions. We want to work incrementally. We want to break up the problem into pieces and be able to work on it in different, at different paces in different areas. We want to carry out experiments and consciously design the experiments, which I think is one of the things that Dave was talking about in his presentation, which is to think, take seriously the idea of what you are doing whenever you release a change into production is a form of experiment. Is this going to have the impact that I desire? Is it fast enough? Is it scalable enough? Is it resilient enough? Is it valuable enough? Is it giving me the commercial returns that I want? Those are the things that we're really interested in if we want to do a great job. And last in my list was being empirical. So using the real world data to inform our decisions and to guide our forward forward plan. So software development is also, as well as learning, is about managing complexity. We build software that is beyond the capacity of a human being to hold in their head in one stage. So we also need to think about how we can manage the complexity of the systems that we build. And this goes to some fairly, to my mind, fundamental principles of what software development in the real world is about. You know, it's about modularity, it's about abstraction, it's about separation of concerns, coupling, managing appropriate levels of coupling in our designs, and cohesion. Talking to you, the microservices group, you know, this stuff should be intimately familiar to you, because this is what microservices is about. It's about trying to decouple the work of different parts of an organization so that they can work more independently of one another. That's what microservices was invented to achieve, and it uses these sorts of technical qualities, properties, approaches to be able to accomplish that. So when we start talking and thinking in these sorts of very abstract terms about what it is that we do, the idea of information is a little bit slippery. These ideas are just as true of the organizations in which we work and operate as the software that we create. The organizations that we work in are information systems too. And so ideas like concurrency and coupling cause problems in organizations at least as much as they do in software. So we need to think about all of these issues, these ideas of compartmentalizing things, at the organizational level as well as at the software level. So what do we need to do? We need to recognize that software development is a creative discipline. We need to think very cautiously about the cost of those things that create problems, things like coupling in our organizations, in our software. Dependencies in code and in organizations are caustic, and they are the stumbling block nearly all of the time. We need to apply, I think, engineering thinking to solving these problems. And by engineering, what I mean is not a kind of simplistic view of engineering essentially equaling the code that we build or the technical aspects. Engineering, if you think about what it really means, it's the process of solving problems. We engineer a solution to a problem. I've just posted a video on my YouTube channel while we've been talking here about SpaceX, comparing software engineering to the engineering that's happening inside of SpaceX, because, you know, this is a creative act. Engineering in that sense is a creative act, and you know, you need to iterate and get feedback and learn and all of those things that we've been talking about to achieve engineering in any discernible way. So we need to think about optimizing for learning. We need to optimize to limit the complexity. If we want to do those things, then we need to take control of the variables. We want to be able to get repeatable, reliable feedback from our systems. We want, if we deploy the system into production, we want it to work because we've tested that it worked, and we did that by doing things like infrastructure as code. We want our tests when we run them to give us the same results every time that we run them, however many times that we run them, and so on. That starts to move us more in the direction of a more engineered kind of outcome. We want to make more evidence-based decisions, and that gets to this idea of being more experimental in the way in which we approach solving problems. I think a slightly more subtle thing that I think that we can learn and adopt from, you know, science and engineering is that we start out by not assuming that we have the correct answers to these things. We start off largely by assuming that our answers are probably wrong, and therefore we're going to try and figure out how they are wrong. That's a much better way of designing our experiments. This allows us to start using techniques that science learned sort of in the early part of the 20th century of falsifiability. How do we falsify our ideas? If you think about an automated test for a piece of software, it makes most sense when you think about it as a falsification mechanism. Your test is telling you nothing when it's passing, but as soon as it's failing, it's telling you that your software is not good enough. I think there are some important tools that allow us to to apply this kind of thinking and this kind of approach to software development. And these tools are striving for testability and striving for deployability. So let's look at those in a little bit more detail, and what is it that I'm talking about. So what are the things that we value in good code? What are the things that make it good? What do we recognize as being quality in code? Well, first and fairly obviously, it has to work. Next, things that I've already mentioned. It needs to be modular. We need to be able to compartmentalize the code so that we can kind of think about it in pieces. And it needs to be appropriately coupled. I've put loosely coupled here. Loose coupling is not always the right answer, but it needs to be coupled to the appropriate degree so that we've got some flexibility with the systems that we build. It needs to be cohesive. My favorite description of good design comes from Kent Beck, who said that good design is moving the stuff that's unrelated further apart and putting the stuff that is related closer together. And I think that's kind of mildly funny, but also quite accurate in terms of what high quality in design really is. It needs to have a good separation of concerns. We need to think about the levels of abstraction within a piece of code and be consistent in those levels of abstraction. And our code should be focusing on doing one thing and one thing well. And then it needs to exhibit information hiding. We want to be able to consume other pieces of code without knowing all of the detail of how they work. This is deeply important, certainly when you start thinking about, all of these things are important when you start thinking about microservices approaches to architecture. So I'm going to whiz through some brief descriptions of these very quickly. I'm not going to read out all of the slides, but modularity is important because it allows us to decompose the problem into smaller, simpler chunks. The solutions are more independent, they're more composable, and often more scalable as a result of improving the modularity in the code. Appropriate levels of coupling, loose coupling, it tends to reduce the risk of change in one place affecting another part in the code. That helps to isolate problems, limit the blast radius, as Dave was talking about in his presentation, aids the modularity of the systems, and helps us to decompose bigger problems so that they're more understandable, easier to deal with. High cohesion. We want to focus reduced module complexity, and all of the bits that are related are close together. That improves the maintainability of the code. It makes the code easier to read because all of the stuff that you care about is there in front of you, and that tends to allow us greater opportunities for reuse when that's applicable. The separation of concerns is really a slightly different class of thing in that this is a technique that helps us to improve the modularity and cohesion and reduce the coupling in our designs. It's classically represented as the phrase kind of one class, one thing, one method, one thing, one function, one thing. But it simplifies development. It gives us focus again. It helps us to reduce the coupling and improve the modularity. And it simplifies the maintenance and testing and improves the composability of the systems that we create. And information hiding, I don't mean this in the kind of, OO only sense. What I mean is hiding secret. Our code should keep secrets. It allows us to, using abstraction, allows us to establish points of stability in the design that can change more independently of one another. Again, this tends to reduce the coupling, improves the cohesion, aids the modularity and separation of concerns. So let's think about what it takes to put those things into code. In the absence of test-driven development, I would say that the only thing that it takes is the skill, experience, and integrity of an individual programmer. It's a choice. It's a personal choice to decide whether you're going to build high-quality code or not. Test-driven development is one of the most significant changes in my career from my point of view. And it's best characterized by this simple little kind of mantra: red, green, refactor. Red, we're going to write a test, run it, see it fail. That's red. We're going to write some code to make the test pass, run it, see it pass. That's green. And then we're going to modify the code and the test to make them beautiful, readable, elegant, more generic, and so on. That's refactor. This is kind of a good description of test-driven development. Test-driven development is always start by writing the test first. If you don't write the test first, it's not test-driven development, it's something else. Think for a moment what it takes to achieve that. If I'm going to start off by writing my test first to make my code testable, then what does testable code look like? Well, it has to work because we've got a test and the test is going to say that it works. It's got to be modular because I need to be able to test pieces of the code, not the whole thing together. It needs to be loosely coupled so that I can test these pieces in isolation from one another without a horrible job of trying to build up complicated bits of code. It needs to be cohesive. It needs to be focused on delivering some nice, beautiful outcome, and it needs to have a good separation of concerns, and it needs to exhibit information hiding. What test-driven development does, the reason why I value it so highly is very, very little to do with the tests. It's the act of creating them and the way of organizing the work. What test-driven development does is it kind of works as a sort of talent amplifier. Before test-driven development, it was just down to the skill and experience and commitment of the programmer. After test-driven development, if we practice test-driven development, that's going to encourage us to create more modular, more highly cohesive code with better separation of concerns that's more abstract and more loosely coupled with other parts of the system. So the combination of these two, we don't discard the skill and experience of a programmer, but we amplify that talent through this technique. So test-driven development and the skill of a programmer kind of makes the programmer's output better. It's not going to make a bad programmer great, but it'll make a bad programmer better, and it'll make a great programmer greater. So it's unusual in our experience of software development. It is this kind of talent amplifier that helps us to get a better outcome. There's not very much in software that does that, really, if you stop and think about it. I'm going to go through very, very quickly some very simple code. If you're not a Java programmer, it doesn't matter. This is written in Java, but I think it's such simple Java that it's easy to understand. But I just want to try and describe a little bit of what I mean when I say that it drives these properties into the code that we create. Here's a car. Here's a class that represents a car, and this class has an engine called a petrol engine, and this is a start method. So the start method says that we're going to put the gears into neutral, we're going to apply the brakes, and then we're going to start the engine. So let's write a test for that class. So here's my test. We're going to create a new car. We're going to say start the engine, and what do we do now? It's the engine's private. There's nothing that we can assert that says whether the engine started. So that's not very good. So let's try and make our code a little bit more testable. Here's a better car, and it's different from the original car. Specifically here, instead of creating the engine, we're going to inject the engine. And we're going to do this to make our life easy in writing a test. The rest of the code is the same. That's the only change that I've made. So using dependency injection, I've bunged an engine, I passed an engine into the car. So now we could write a test. So here's a fake engine, and we'll come back to that in a sec, which I'm going to pass into the car. Here's the fake engine. So when start is called, we're just going to update a Boolean flag, and then we've added an extra method that says reports on the value of that Boolean flag. That's all it does. If you were doing this for real, you'd probably use a mocking engine or something like that. But I just wanted to write the code so to keep it all simple as an example. So we're going to create our fake engine, and then we're going to create our better car with that fake engine. And now we're going to say start the car. And now we can say, did the engine start successfully? That's my test. So making the test, making the car, the better car testable has changed it in some important ways. Let's just think about what that means for the design of the better car for a moment. So if I wanted to create a car now, I could create a better car that still had a petrol engine just as before. But just as easily, I could create a new, better car with an electric engine without changing the better car at all. So my code, with that one small change, is more flexible, more composable, better contained, more testable as a result. It's more modular, more cohesive. All of those things that we talked about, it's improved just a tiny bit for this one simple, trivial class. If I was crazy and I wanted to invent a jet car, I could create a car with a jet engine. No changes to the code. So test-driven development allows me to amplify the talent of a developer. The other attribute, the other technique that I talked about, the other strategy for doing this is deployability. And working to make our systems deployable gives us some great properties too. This is the picture that I tend to use for a deployment pipeline. And lots of people kind of misunderstand what continuous delivery and deployment pipelines are about sometimes. But my view of deployment pipeline is that a deployment pipeline always goes from commit to a releasable outcome. We're going to optimize to make that efficient, automated, fantastically quick as much as we can to get great feedback and insight. And we're going to put our changes into this drip, 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 many small changes, and evaluate those changes fast and efficient, but always to a releasable outcome. Now, if we want it to be releasable, that means it's got to be deployable too, because we've got to be able to put it into release. So what does deployable mean? It means that there's no more testing to be done after we've got to our releasable outcome, because it's releasable. So there's nothing more to do. There's no sign-offs. There's no integration tests with other components of the system. It's got to be an independently deployable unit of software. That's the focus of continuous delivery. We have to take these ideas seriously to achieve this. Modularity, information hiding, separation of concerns, abstraction. This is deeply what microservices is about, for sure. These things. The point of a microservices is primarily it's an organizational scalability play. It's to decouple teams to the extent that they can work independently on their services that they're responsible for. That means that those services need to be independently deployable of one another. So these are the principal tools that allow us to scale up software development. If you want to be Amazon and grow phenomenally at a more efficient rate than most other organizations in the history of the world, then what you do is that you build yourself out of many small independent teams working on software that is independently deployable and decoupled from one another. So, scaling. What does scaling mean? We can think about scaling the size and the complexity of the systems that we create, and we can scale the size of the organizations to create them more quickly. No, we can't do the second one. What we do is that we scale up the number of independent teams if we want to do that. We scale up by focusing on going smaller. You can't make a baby in a month with 9 women is the famous quote from Fred Brooks that he wrote in the Mythical Man Month in 1970s. There's a degree to which you can't parallelize a problem infinitely. There are hard constraints that stop you doing that. So the more that you try, and as soon as you start to bring these things back together, to test them together, to evaluate them together, whatever that might mean, the more problems that you tend to face. So if you want to be able to, if you want to average out creating a baby in a month, then you need nine women in 9 months, and on average maybe you can do a baby in a month, but you can't do it for one thing. You've got to deploy it independently. There's great data on the importance of small teams. I'm going to whiz past this. There's a link in here. I'll try and get the slides to you via the organizers, but the data fundamentally, the quick synopsis of this data is they did an evaluation of teams of fewer than 5 people, teams of over 20. The teams of 5 people took, they measured how long it took each team to get to 10,000 lines of code. The teams of 5 of 5 and fewer people did it in 1 week longer than the teams of 20 people over a period of 9 months. So a team of 5 people is nearly 4 times as productive as a team of 20 people. So you need to, or if you want to scale up, you need to organize your, you want to structure your organization around many small teams. So organizational scaling, I'm going to whiz past this, but this is about space filling networks. If you have a structured hierarchical organization, which is common, there's some interesting scaling factors. If you double in size, you're going to not double in commercial impact or productivity. You're going to improve commercial impact or productivity by about 85%. There's another way of organizing, and that is the more distributed way, the kind of social network way. You have many small networks that are very loosely coupled to one another, and this is how Amazon works. And the scaling factor for Amazon is deeply unusual. If Amazon doubles in size, it will increase its commercial output and its productivity by 115%. So Amazon more than doubles in its output as it doubles in size. That's very unusual in economic terms and in business organization terms. And it's down to the maths of organizational scaling around this stuff. Fascinating stuff. If you want to read more about it, there's some stuff to Google here. So to scale up problem solving, problem solving needs to be distributed. We can't have hierarchically directed graphs of communication telling everybody what to do. We need small independent teams that figure out the problems for themselves. That's how you scale up. This is about, a very different way of organizing the firms in which we work. What does this mean in terms of individual teams? If we've got an autonomous team, they're going to be working on their own stuff, having their own deployment pipelines, getting feedback, deploying their own software, directing their destiny, thinking about the business impact of the stuff that they're working on, the services that they're working on, independently of other people. The goal of leadership in these sorts of things is not to tell people what to do. It's to kind of set strategic intent. We're heading off in this direction. We don't know how to do it, but you're smart, figure it out. And then kind of give boundary parameters. Here's your budget, you go and solve the problems. And then there's kind of platform support to allow those teams to retain their autonomy. And that's really about tactics and common tools to just take the drudgery away from the autonomous teams. You can think of the cloud as a good example of doing this bottom part. They're trying to deliver those tactics and the common tools to allow the autonomous teams to focus on the value that they are trying to deliver to their customers and users. So techniques to breed autonomy. How do we go about doing this? I've already talked about aiming for testability and deployability. There's another one that I like to. We want to try and keep people focused together at an abstract level, and I like this idea of whiteboard models where we're going to have a high level picture of the system that we're building. The idea here is to try and establish a common consensus so that if somebody came and asked any member of the team, where would you put this feature, they'd all come up with very similar answers. So you've got some kind of a tourist map of the workings of the system. The goal for these sorts of things is not to go into too much detail, consciously avoid detail, which is why I call them whiteboard models. The idea is that any member of the team can recreate this model of the system on a whiteboard from memory, and that kind of puts a cap on how complicated it can be. Pair programming is another technique that spreads learning in a team. It allows teams to grow. Actually, pair everything. People are more creative when they are working with other people, and so that too amplifies learning in organizations. The primary role of leaders in these sorts of organizations is not to command or instruct people what to do. We scale decision making by making it pervasive, distributed, and continuous everywhere throughout the organization. And I think in large part that's really what microservices as a strategy is focused on trying to accomplish. Thank you very much. That's the end of my talk. So I hope I've managed to do that in the right amount of time, and hope we can get to some questions. I just point to some links. I have a YouTube channel, which I've mentioned a few times. There's a link here to the YouTube channel. There's some good content there around this kind of engineering theme. Let me just go back and turn off the screen sharing. Cool, thank you. Any questions?
Thank you. Any questions for Dave?
Yeah, I've got a quick one, actually. The book you showed, that book, actually, from where I can get that book from?
The book that I showed, you can buy it on Amazon. It's called Continuous Delivery.
All right, thank you.
That's okay. I have another book that's about to be released that you can search for on LeanPub, which is called Continuous Delivery Pipelines. It's kind of a manual to help you create deployment pipelines.
Awesome.
I could go on. When you're talking that last slide around scaling decision making, what kind of techniques do you use for that? And how can you do that in a safe manner? Because that's kind of what I see in a lot of teams, whereby we want to have autonomous teams, but then they don't have the tools or the ability to kind of get things into production safely.
So I think that's one of I whizzed past some of the ideas because I was, if I'm honest, that was a 45-minute presentation that I gave you in 30 minutes. So the pair programming, one of the reasons that I put that up, and I think that's important, is because it starts to breed that autonomy. It allows pairing allows people to learn the skills that they don't have to accomplish some of these things. There's certainly part of the paradigm shift that is essential for particularly traditional larger organizations to let go of that sense of control to some degree. The simplistic answer, which is kind of interesting, is that you lose that control. You delegate that control, the decision making, to these small independent teams, and you allow them to make their own mistakes, and sometimes they will. There's some fascinating stuff. If you look at AWS, last year I saw an estimate from Sam Newman last year that they released nearly, I think it was nearly 2,000 different changes via AWS. Some of those things are duplicates. Some of them are incompatible with one another. Some of those things are never, nobody's ever going to use, or not in any significant numbers, because they'll be wrong. But that's how you learn. You try these things out and you figure out what works and what doesn't. That means you've got to be willing for some things not to work. And so organizationally, the challenge is, the paradigm shift is to give up some of that more centralized control. And to facilitate that, you need to educate people and help grow their talents and their skills. For organizations that have already done that kind of thing, the commonest feedback from them is that actually it's not as big a deal as you think it is. There's the famous quote from Adrian Cockcroft, who was the CTO at Netflix, and he said that people used to come up to him and said, "Oh, you're so lucky. How do you get the fantastic engineers that you've got at Netflix?" And he said, "Well, mostly we hire them from you, and then we get out of their way." And this autonomy is important. It's a measure that the data is fantastic. If you look at the Accelerate book, the State of DevOps report, the data says that one of the key predictors for high performance in terms of measures of stability and throughput is that a team is able to make its own decisions without coordinating with anybody outside of the team. So small autonomous teams produce higher quality work. They do it more quickly and more efficiently, and generally the software that they create is likely to please users more, as long as they kind of drink the Kool-Aid and take this more experimental, evolutionary approach to software development.
Okay, great. Thanks for that.
Pleasure.
So you have mentioned that the team leads are not there to tell others what to do. Then what would be their role within the team then?
I think that the key idea. So I spent the vast majority of my career working as a team lead or as a technical leader on development teams, and what I came to see my role as is largely two things. One was to kind of be a technical tiebreaker. If the team couldn't make a call on which way to go for some particular issue, I'd make the call. My vote counted a little bit more than other people on the teams, and so I'd swing the balance on those decisions if they couldn't make it, if they couldn't decide it for themselves. And the other part of my role was to essentially coach the team. So I think about team leadership rather. I'm a football fan. My team is Manchester United, and if you are Ole Gunnar Solskjaer or better, Alex Ferguson. If you were Alex Ferguson, he was by the time he finished being the most successful manager of all time, he wasn't the greatest footballer. He was in his 70s, but his job wasn't to be the best. It was to coach, hire people who were better than him, and to get the most out of those people. So I think that's really the role of a team leader. And any sort of technical leadership, to my mind. Sure, you're not going to dump all of your experience and your talents. You're going to have the conversations, you're going to take part, but it's not your job to impose your will on the team. The idea is that the team as a whole grows in capability, and collaborates effectively, to my mind.
Thank you, David. Awesome. Thank you so much.
Any more questions? I could have done the 3/4 of an hour version of this talk at this.
Sorry, I have a question about the organization chart. I was just wondering, what is the chain of command? I think you show us the Amazon version, and then the default for the common version, which tends to have a hierarchy level. I think the Amazon one tends to be coupled. I'm just wondering what is the chain of command in the decoupled version? I mean, who makes the final decision? I mean, one of the reasons why we tend to go for the triangular organization chart is for someone to have the major final say. I'm wondering how that works in the structured.
There are different strategies for organizing things. In most of the projects that I've worked on for the last couple of decades, I've been one of those people, the technical leaders in the team, and mostly the kinds of software that I worked on, it wasn't completely decoupled in the way that I described with Amazon. In Amazon, it's the team's responsibility, and there will be leaders with there'll be a hierarchy within the team in terms of there will be more experienced people in the team that kind of whose opinion has greater sway and all that kind of stuff. But largely in those sorts of teams, it's largely self-organizing. For the kinds of software that I spent the latter part of my career largely building trading systems, low latency, high frequency trading and all of that kind of stuff. And for those sorts of things, you do need more kind of consistency, coherence in the systems to achieve the levels of performance that we're aiming for. And so one of the strategies that we usually applied is that we'd have these small independent decoupled teams. And there would usually then be kind of a scrum of scrums or a cell of cells, a kind of federated group of people who led certain roles within the team. So my group of people were usually the tech leaders in each of the teams. They were my crew, if you like, and we'd get together on a regular basis and we'd have conversations about the technical issues that impacted on the development as a whole, and we'd come to some kind of consensus. As I said before, my job then was to coach the decision making, sort of facilitate all of these things. And in the event of a tie, if nobody could decide which way if the group couldn't decide which was the right way to go forward, then I would make a call and decide. So that's the kind of leadership role that I think works very well up to a certain limit of building large systems. That works. I've done that up to kind of, you know, medium hundreds of people working on a project, low thousands maybe. If you want to go bigger than that, if you want to go to a massive scale, you've got to be more independent than that.
Awesome. Thank you. Yeah.
Pleasure.
Any more questions?
I think there's some questions in the chat.
Any tips to sell the practice of TDD to colleagues? I'm sorry to keep pushing my YouTube channel. There's some stuff on the YouTube channel that talks about the reasons why TDD is important, why it's good. I'm working on editing a video that will be published probably next Wednesday on some TDD patterns and how to use it to drive design better. That might be so actually they're anti-patterns. So what does bad TDD look like, which might be useful as well to help people think about those sorts of things. So I think there's some stuff like that. My usual advice for people to give TDD a go is to look at something like cyberdojo.org, which is a website that allows you to practice TDD skills around very simple coding exercises, little coding katas. And it supports a whole bunch of different technologies and gets a bunch of different coding katas, and it just makes it really simple to try that out. Go there, and my advice is pick one coding kata. Pick something like FizzBuzz or adding fractions or something like that, and do that repeatedly using the red-green refactor discipline religiously for a couple of weeks, 30 minutes a day for a couple of weeks. Start your day, every day, with 30 minutes of just practicing TDD. At the end of that, you'll understand better about why this matters, how it works, what works, in my opinion. What else is there?
Hey, Dave, what was that URL? What was the name of the site?
It's cyber-dojo.org. CYBER-DOJO. Yeah, somebody's put it into the chat. Thank you. So somebody's posting their experience of TDD, and it's. I said in my talk. I think it's one of the most profound things that's happened during my career. And remember, I saw the birth of the World Wide Web. But what I mean is in software development terms. I think that there's not very much in software development that we can think of as real engineering in the sense that it amplifies, it has a direct impact on the quality of our work. And I think that TDD does. And I think that that's really, really important. And it kind of saddens me. TDD is still growing. It's still widely practiced in lots of different teams, but it's still not everybody, and it's probably not even most, which I think is a shame. I think that quite a lot of the problems that we see in software would be almost eliminated. There was some great academic research that was conducted probably about 3 years ago now, where they did an analysis of production failures. They looked at what was happening in the code at the point at which there was a defect in production across thousands of different projects. And what they found was that 58% of the defects were the kind of mistakes that every programmer puts into code in every language, off by one errors, conditionals the wrong way around, scoping problems with variables, all of those common mistakes that if you've ever written any code at all, you'll recognize. Those are responsible for 58% of production defects. And if you do simple TDD, you eliminate all of those. Think how much effort you save if you eliminate nearly 60% of the defects in production. Think how much nicer your work experience would be if you only had 40% of the defects that you normally have. So I think TDD is really important, and as I say, I think it saddens me that it's not more widely adopted. Yes, Dave's just mentioned, would I agree that technical debt is far less likely to accumulate in a TDD environment? Yeah, absolutely, I would. I think that what TDD gives you, particularly when it's done with some skill, is it allows you to groom the code all of the time. The nicest code base that I worked in was when we built one of the world's highest performance financial exchanges. It was a beautiful code base, and it wasn't beautiful because we started out with it being beautiful. It was beautiful because we changed it all of the time. We were kind of gardening it, we were grooming it all of the time, changing it all of the time, drip, drip, drip changes all of the time. And it got better and better and better to work on over the period that I was working on it. And that, we don't think of code like that very often. Where would be better to start implementing the TDD via unit tests or integration tests? It's easiest at the unit test level and test first. I talk in terms of testing strategy about 2 levels of testing, and they are both complementary. To really do it well, I think that you need both. You need kind of at the higher level acceptance testing, which is kind of BDD style, executable specifications that define the behavior of the system, and then the lower finer grained test driven development. Every line of code that you create in your production code ideally is demanded of you by a failing test, and that's true test driven development. There's quite a lot of stuff on my YouTube channel talking about both the low level fine grained TDD and the higher level broader BDD style executable specification things that describe the kind of approach that I've used. The system that I described, which we were building while I was in the middle of writing the continuous delivery book, so I was kind of continuous delivery from day one. Fantastically complex, high performance system, one of the world's highest performance financial exchanges. It was built exclusively using these techniques. Big, complicated system, processing terabytes of data a week. It was fantastic system to work on, and that's to my mind as part of this engineering approach of applying TDD. I'm not quite sure what the question. What does USI method in introduction of new design features like user-friendly products? If you want to elaborate, I'll try and answer the question, but I'm not quite sure what you mean.
I think that was meant to be using this method. What about using this?
Sorry. Okay. What about using this method in introduction of new design? Yeah. Okay. So absolutely. So that's where it comes into play. So if you start from scratch, that's the best way of adopting this practice. TDD is a bit more tricky as a retrofit. Again, I'm really sorry that I keep touting my YouTube channel. I have some videos on what you do when you're not starting from scratch, refactoring legacy code to testability. But TDD is ideally you start from the beginning using that approach. And when you do that, that's when you really get all of these advantages that I've been talking about. The outside-in design approach of the red-green refactor thing is really impactful on the design of the code.